In this class, we will discuss about Gibbs paradox. So we have already discussed the entropy for ideal gas, and we will use that equation here, and we can write the equation for entropy as S equal to n ln V plus 3 by 2 nk plus 3 by 2 nk ln 2 pi mkt. Okay, so this is the entropy equation for an ideal gas. Okay. Now, from this entropy equation, let us consider two ideal gases, and they are separated by a wall. So the condition is like this: we are having two ideal gases separated by a wall, and this is an impermeable wall. So that the number of particles will be fixed on each side, and this side we are having number of particles n1, and this side we are having volume v1. Okay, those are fixed, and the temperature on both sides are same. Okay, temperature is same. So let's consider the number of particles on this side is n2 and the volume is v2, and the temperature is same, T. So temperature is same, but the number of particles and volume are different here. So let us consider this system, and in that case, if you consider what is the entropy of the gas in this chamber, that can be represented as S1, and the entropy in this chamber can be represented as S2. Okay. So the first gas is having entropy S1, or the gas which is in the first chamber, which is S1, entropy S1, and the second chamber corresponding to second chamber, gas in second chamber, we consider the entropy as S2, and then we can write S1 as S1 equal to N1K, because N1 number of particles are there, okay, for the first case, or in the first chamber. So N1K ln V1, you just have to substitute the number of particles, temperature, volume, etc. in this expression, in the first expression, that is the entropy equation for ideal gas. So in the first case, we will be having S1, that is equal to N1K ln V1 plus 3 by 2 N1K 1 plus ln of 2 pi mkt by h square. So we have taken 3 by 2 nk as common here, 3 by 2 nk is common, and then you can write it as 3 by 2 nk into 1 plus ln 2 pi m. So here also we are having m1 kt. So the mass is m1 for the first case, and the second gas is having mass m2. So then here we are considering the in the bracket term, you can see this is 1 plus ln of 2 pi m kt by square, that is multiplied with the 3 by 2 nk. Okay, 3 by 2 nk. So that is this whole term. Okay. Now, if you consider in the case of second chamber, or the second gas, then that is S2. Entropy will be S2. For the second gas, entropy will be S2 N2K ln V2 plus 3 by 2 N2K 1 plus ln 2 pi m2 kt by h square. Okay. Simple expressions. You just have to substitute a number of particles, volume, and temperature here, and mass of course. So those will be substituted for each gases, and you will get S1 and S2. And the total entropy, if you are considering the entropy of the whole system, then you can write the total entropy ST as S1 plus S2, which is equal to N1K ln V1 plus 3 by 2 N1K 1 plus ln 2 pi m1 kt by h square plus n2k 3 by 2 n2k into 1 plus ln 2 pi m2 kt by h square. I think I have missed one ln v2 here. Okay, we have ln V1 here. So similarly, we will be having ln V2. So this is N2K ln V2, 3 by 2 N2K, 1 plus ln 2 pi M2 by KT, M2 KT by H square. Okay. So that is the total, which means that the total entropy of the whole system. If you consider all this whole system, if you consider, then the total entropy will be S1 plus S2. Now, if you remove this barrier, the center one, if you remove this barrier, okay, then if you mix these gases, okay, if you mix these gases, so that the number of particles from this side can go this side, and number of particles from this side can go the other side, and mix all the molecules of the gases, all the particles of the gases, then what will be the entropy? So in that case, what we have to consider, the total number of uh, particles in the whole system. When you remove that barrier, when the two gases mix together, and then in that case we have to consider the number of particles as total number of particles. Okay, then your expression will become entropy after mixing, that is Sm, that will be equal to N1 plus N2, that is the total number of particles, times K ln V1 plus V2, that is the total volume of the system, V1 plus V2, plus 3 by 2. Then you have N1 plus N2 times K, plus 3 by 2 N1K ln 2 pi M1 KT by square, plus 3 by 2 N2K ln 2 pi M2 KT by H square. Okay, you cannot take N1 N2 N1 plus N2 here, because you are having different masses, N1 and N2. They are not common. Okay, so all the expression with the n, that is replaced with the n1 plus n2 here. You can see instead of n we are having n plus n2, and all the v we have, instead of v we are having v1 plus v2. And same expression in the first equation, you have to substitute all those conditions. Then you will get, after mixing, the entropy will be n1 plus n2, that is the total number of particles, times KLN, total volume, V1 plus V2, plus 3 by 2, instead of 3 by 2 nk, we are having 3 by 2 n1 plus n2k, in such a way that n equal to n1 plus n2. Okay, then plus 3 by 2 n1k log 2 pi m1 kt by square, plus 3 by 2 n2k log 2 pi m2 kt by h square. So that is the expression after mixing. Okay, so first we have considered two different gases separated by a barrier. Then in that case we have the entropy of first gas S1, and the second case we have the entropy of the second gas S2, then the total system. Okay, in that scenario the total system will be having entropy St as the total entropy, and that is equal to S1 plus S2, that is this expression. And after that we are removing that barrier and mixing the two gases. Then after mixing, the entropy will become Sm, that is equal to n1 plus n2 k ln v1 plus v2, plus 3 by 2 n1 plus n2 k, plus 3 by 2 n1 k ln 2 pi m1 kt by h square, plus 3 by 2 n2 k ln 2 pi m2 kt by h square. Now if we subtract entropy of mixing and entropy of total entropy, or if we can consider subtracting total entropy from entropy of mixing. Okay, that is nothing but the entropy change in entropy, that is delta S, change in entropy, delta S is equal to Sm, this is Sm, the entropy of mixing, minus St, okay, total entropy. And if you calculate what is the after subtracting this total entropy from entropy of mixing, or entropy after mixing, then you will get delta S is equal to n1 plus n2 k ln v1 plus v2 minus n1 k ln v1 minus n2 k ln v2. All other terms will get vanished. So these terms will get vanished. Okay, so this is the final expression after we subtract Sm and abstract the total entropy from entropy after mixing. Then that is the entropy change in entropy. Okay, Then if you further rearrange this expression, then you can write n1. You can take n1 as common, then you can write k ln v1 plus v2 minus k ln v1 plus n2 you take as common. Here n2, this n2 you take common, then you can write n2 into k ln v1 plus v2 minus k ln v2. That is the entropy change. Now if you further consider entropy, again you can entropy change you can further reduce into n1 k ln v1 plus v2 by v1 plus n2 k ln v1 plus v2 by v2. This is a simple expression. You can see from here in this expression you can see that this k ln, you can see here k ln v1 plus v2 here minus k ln v1. So by the rule of ln a minus ln b, that is equal to ln a by b. So you can write it as ln of v1 plus v2 by v1. Okay, k is constant, so you can take k as common. So if you take n1 k, then you can write ln v1 plus v2 by v1, ln of v1 plus v2 by v1, because ln of a by b is equal to ln of a minus ln of b. That is the relation. So if you take that identity, then you can write the entropy change as delta S equal to n1 k ln v1 plus v2 by v1 plus n2 k ln v1 plus v2 by v2. Now you can see that delta S is greater than 0 if you substitute, because n1 is a positive quantity, n2 is a positive quantity, v1 v2 all are positive quantity, so that this value of delta S will be always greater than 0. So delta S is a positive quantity. So but mixing of two dissimilar gases is a irreversible process. Okay? If you consider mixing of two dissimilar gases, this is an irreversible process, and hence delta S is always greater than 0. So that is true from the thermodynamic point of view. So this is okay. Now if we consider the particle density as same, particle density means number of particles per unit volume. So if we consider the initial case n1 per v1, okay, n1 number of particles in v1 volume and n2 particles in v2 volume. So if we consider equal particle density, which means that n1 v1 equal to n2 v2. If we are considering both the gases having equal particle density, then n1 v1 equal to n2 v2, or you can write it as n1 by n2. You take this n2 to the other side and this v1 to the other side, and then you can n1 by n2, n1 by n2 equal to v1 by v2, or n1 by n2 plus 1, this is plus 1, n1 by n2 plus 1 equal to v1 plus v1 by v2 plus 1. What is this term? This term you can also represent this as n1 plus n2 divided by n2. This is equal to v1 plus v2 divided by v2. Okay. So n1 by n2 equal to v1 by v2 is also, you can write it as n1 plus n2 by n2 is equal to v1 plus v2 by v2. Now if v1 plus v2 by v2, if v1 plus v2 by v2 equal to n1 plus n2 by n2, then you can replace equation 5. Equation 5 becomes, you can see here, this in equation 5 you can see this v1 plus v2. So instead of this v1 plus v2 by v1 and v1 plus v2 by v2, you can replace n1 plus n2 by n1 and n1 plus n2 by v1 plus here v1 plus v2 and v2. So n1 plus n2 by n1 and n1 plus n2 by n2, you can replace those expressions, as you can see from this. So the equation 5 will become delta S is equal to n1 k ln n1 plus n2 by n2 by n1 and n2 k. I think that Yeah, this should be, I think this would be N1. N1 by N2 is equal to V1 by V2. So we can write it as N1 by N2 plus 1 equal to V1 by V2. So in the opposite way, you can also write N2 by N1 equal to V2 by V1 and N2 plus N1. So if you take in that scenario, then this will become N1. Okay. I hope you understood this. If you are considering this term as N2 by N1, in this from this we can write N2 by N1 equal to V2 by V1, or we can also write it as N2 plus N1 by N1. This is equal to V2 plus V1 by V1. So from that identity you can uh, replace equation 5 like this, okay, and then you will get N1 KLN delta S, that is change in entropy, as N1 KLN N1 plus N2 by N1, and then N2 KLN N1 plus N2 by N2. Now, if you consider this scenario also, delta S will be positive as N1 and N2 are positive quantities. So, delta S is still, it is greater than 0, no problem with this equation also. Now, if you consider two identical gases, when you consider two identical gases, identical means they are having same properties, then equation 6 gives delta S is greater than 0. Okay, even if it is identical gases, the number of particles on one side is N1, the other side is N2. So if even if you consider two identical gases also, N1 and N2 will be positive. There is no change in that. So that delta S will be positive. But thermodynamically, if you consider two identical gases, delta S should not be greater than 0. Okay, but from thermodynamic thermodynamics, change in entropy for or mixing of identical gases, if you consider change in entropy for mixing of identical gases, that should be 0. Okay, as it is a reversible process, since mixing of ideal gases, which is a reversible process. Since it is a reversible process, so after sometimes if you take the barrier again, then you can see the number of particles on the other side, both sides, which can be same as the initial case. Okay, so if you are considering two identical gases, I will draw that diagram again. So if you are considering two identical gases like this, with N1 number of particles here, N2 number of particles, V1 and temperature, okay, V2 and temperature. So if you remove this barrier now, if you remove the center barrier, then if you mix that identical gas, and after sometimes you put that barrier again, then you can also see you can see N1 number of particles here, V1 with volume V1 and T, and N2 number of particles here and V2, if they are identical particles. Okay, if they are unidentical particles or non-identical particles, then the sum of the particles from second gas can go here and it will be there, and some of the particles from the first gas will be here. So you cannot uh, reverse the situation. So it is an irreversible process. But in this case, when you consider identical gases, it is a reversible process, and after sometimes you can again construct the same system. Okay. So when it is a reversible process, delta S should be 0. But if you are applying this equation, number of particles is will be a positive quantity, so delta S will be greater than 0. So by equation, we get delta S is greater than 0, but by thermodynamics, we are having delta S is equal to 0 for a reversible process or a mixing of ideal gases, delta S should be equal to 0. So this discrepancy is known as Gibbs paradox. So by using the equation of entropy of ideal gas, we get delta S greater than 0 for mixing of two identical gases, but it is not the case when you consider in realistic situation or thermodynamically if you consider we have to get delta S is equal to 0 for mixing of identical gases. Okay. So this discrepancy or mismatch is known as Gibbs paradox.